Okay, good morning. We continue the lesson of complex numbers with the topic of polar form of complex numbers. Okay, so let me just describe what is meant by the polar form. So I think this lesson will take 2 sessions. Unfortunately, on Thursday we don't have any lesson. It was very good if we could finish this. Anyway, so the complex number that we have, z equals to a plus bi, this is the standard form of the complex number. Sometimes we also call it Cartesian form, okay, or standard form. But now we want to talk about another form of a complex number, which is called the polar form. It's a little bit strange we want to do it, because usually in mathematics we want to simplify things. We don't have the tendency to make things more complicated. This is one of those cases that we want to make some simple, innocent, complex number and put it in trigonometric form, which is more complex. And the reason is that probably will not be clear today, but I just want to tell you shortly that if your goal is to raise a complex number to a fairly high power, the polar form will help you to do it more or less very quickly. Okay, so that's the reason we are interested in making a complex number a little bit more complicated, okay? But the payoff is that it will help me to raise the complex number to fairly high powers fairly simply. Yes, so that's the logic. I will talk a little bit about that, but if you want to have an idea about this. Okay, but I have to start a little bit of abstract things. I cannot motivate you that much. The real motivation comes when you see this in action, how it will help you, okay? But let us try to define some terminologies. One thing about the complex number we learned is the absolute value of the complex number, which is also relevant to this topic. What was that? Absolute value of the complex number is the square root of the real part squared plus the imaginary part squared. In this context, it is common to call it R. So if I have one complex number z, in that context, I denote its absolute value by little r. Okay, but then do you remember a complex number can also be visualized as a point on the complex plane. The complex plane is the plane whose horizontal axis, which we call real axis, and the imaginary one, the vertical one is the imaginary axis. And let us say that this point is A, this point is B. Then I find this point there. That is the point representing this complex number. Okay, and now if you take this point and connect it to the origin, you can denote it by that vector. If I ask you what is the length of this blue vector, that is exactly the absolute value. That's the distance from the point to the origin, and that is exactly the absolute value, or in this context I call it r. Okay, there is one new terminology that I want to introduce, and that is the angle that this blue vector, the vector representing the complex number on the complex plane, makes with the positive part of the real axis. And this angle is theta. This angle has a name, and it is called the argument of the complex number. Okay, so theta is called the argument. I will also talk about this article there, the argument of z. And of course, we denote it by these letters A, R, G for argument, and then we put Z there. Okay, but why I emphasize on this there? Because there are different conventions of the size of this argument. In more advanced books, you take that convention from minus pi to pi, which I think it is a little bit confusing in high school. So we stick to the convention in the book, which is from 0 to 2 pi. Okay, or if you want, you can also express it in degrees. And it is important to realize that equality is here for 0, but not there for 2 pi. And the answer is clear, because if this vector is on the real axis, theta can be visualized as 0 degrees, or it can be visualized as 360 degrees, but by convention we choose the 0 degrees. Yes? So when I say the argument of complex number, I mean the angle in this interval, so that the vector corresponding to the complex number makes with the positive part of the real axis. Okay? So let us try to give some examples. For example, if I tell you z equals to I, and I ask you what is the argument of z. So what is the argument? So you need to visualize this. So you need to find the point corresponding to I. I don't want to write all these things, I want to do it faster. So where is I? I, for example, is 1 unit here. So this is the point corresponding to I. If that is 1, then this point is the point I, yes? And then if you connect the origin to that, and then you construct this vector, the angle in this interval or that interval, so that this vector makes with the positive part of the real axis, is called the argument of z. So what is the argument z? Yes? Pi over 2. You can say 90 degrees, but let us work in radians, okay? So the answer is pi over 2. Very simple idea. For example, if I ask you z is equal to a square root of 3, what is the argument of a square root of 3? Where you need to find where the z is. Square root of 3 is only a real part. So let us say that this length is a square root of 3. So this is the vector connecting the origin to this point. And then you want to see what is the angle between this blue vector and the positive part of the real axis. What's that angle? 0 degrees. So this is the argument of this angle. This number becomes 0. Okay? So I don't know, for example, what happens for z equals to minus 5? It's pi, yes, because where is minus 5? For example, let us say that here is minus 5, and then this is the vector connecting the origin to minus 5. But then when I say what is the argument of minus 5, you have to start again from the positive part of the real axis, exactly like trigonometry, and then move up to here. Then it becomes 180 degrees or pi. Yes, so the argument of this complex number is what? Pi. Yes, and I will of course give more interesting examples. Let's just finish this. Okay, and if I go, for example, to z equal to minus 2i, what is the argument of this one? Minus 2i is where is, for example, 1 unit, 2 units. This is minus 2i, yes, minus 2. This point is minus 2i. So this will be the vector. And then if I ask you, what is the argument? That's what I'm saying. You can say minus 90 degrees, but we are not using that convention. So we are using this convention. So what is the answer then? 270 degrees or 3 pi, because this will be the answer. Yes? If you say minus 90 degrees, it is not wrong, but it is a different convention. Yes, we are not using that convention. We are using this convention. So when I say what is the argument of this complex number, I expect you to write what? 3 pi over 2. So what happens if z is 7? If z is 7, don't say 360 degrees, yes, because 360 degrees is excluded. When I go back to the positive part of the real axis, I should say 0 or 0 degrees. Is that clear? Okay, let us write another more interesting one. So what happens, for example, I give you this complex number, 1 plus I, and I ask you what the argument is. So the first thing that you have to do is to understand where this point is. You don't need to be precise, just try to sketch something for yourself to understand that. So this complex number is where? 1 unit on the real part, 1 unit on the imaginary part. So this is my complex number z. And you draw this vector, and then you measure this angle, or calculate this angle. So what that angle here is? pi over 4 or 45 degrees, yes, because that's in square. This length is 1, this length is also 1. So it is very simple to say that argument of this complex number 1 plus I is just pi over 4. Okay, so what about this one? Z equals to minus the square root of 3 plus 3I. Okay, so let us do that together. So first of all, you need to imagine where this point is. Okay, so you don't have to be precise at all. You just need to convince yourself. So, oops, sorry. I should make this one bigger a little bit. Okay, so here, minus the square root of 3. So let us imagine that this is minus the square root of 3. And this should be 3 units. So let us say that this is 3. And then I find this point, and then I connect it to the origin. It makes a vector for me. Oops. Okay, so this is something like that. This is my vector. But be careful. Which one is the argument? Not the small one. Always you have to start from the positive part of the real axis, yes? So this theta we need to find. Okay. You have to convince yourself what theta is. So I don't want to teach you exactly what to do, but one way to do is to use this formula, tangent of alpha. Alpha is not necessarily theta. You can use this as absolute value of the imaginary part of z divided by the real part of z. This formula is not in the book, but it is probably a good way to understand that. So if I calculate tangent alpha, can you tell me what angle alpha is in this picture? Because I am taking absolute value, so I am caring about the length. So if I ask you what this is, you will tell me this is absolute value. Imaginary part is 3. The real part is minus the square root of 3. But because of this absolute value, this minus sign goes away. It becomes 3 over a square root of 3. So this number is famous. Of course, in this form, it might not be famous to your eyes, but instead of 3, you can write square root of 3 times square root of 3, which is 3, and then divided by square root of 3. One of them is gone, and then you get square root of 3. And I hope that you understand, you remember that that's a famous angle. So alpha is an angle, but it is always an acute angle. Why? Because by putting absolute value, the output of tangent is positive, so it should be in the first quadrant. I say, I'm looking for an acute angle whose tangent is equal to a square root of 3. So if you look at the table or using the calculator, alpha is how much? Alpha is an angle whose tangent is square root of 3, and that is 60 degrees or pi over 3. Okay, but which angle is this on the picture? Because this is this angle. Why? Because if I ask you to write tangent alpha, what do you write? You write the length of the opposite side, but what is the length of the opposite side? Is 3, divided by the length of the adjacent side, even though this is negative, but the length is positive, the square root of 3, which is that number. So alpha that you calculate here is this angle, but that is not your question mark, because your question mark theta is the angle that the vector makes with the positive part of the real axis. So what is theta then? Very simple, yes? Pi minus that angle that you found, okay? So what you say here is that the argument that I am looking for here is pi minus pi over 3. You calculate it, it becomes 2 pi over 3. So I can say that the argument of this complex number is 2 pi over 3. Okay? So what about this one, for example? So let me write z equals to minus 1 minus square root of 3 times I. So I want to find the argument of this complex number. So the idea is the same. So what should I do? I need to find where this point is located. approximately. So the real part is -1. Let us say here is -1. The imaginary part is minus a square root of 3. It's a little bit bigger. So, and this is my angle. Yes? This is the vector. But what is the angle that I am looking for? The argument. The argument always starts from the positive part of the real axis and goes to this vector. So this is the angle that you're supposed to find. Okay? But use the same formula here as well. So tangent alpha is what? Is absolute value of the imaginary part, which is minus a square root of 3 divided by the real part, which is -1. So simply it becomes the square root of 3, and alpha is again pi over 3. But which one is this alpha? Which one is that? That is exactly your alpha, this part. Why? Because if I ask you what is tangent alpha, you will tell me this is the length of the opposite side, which is the square root of 3, divided by the length of the adjacent side, which is 1. So that is your alpha. So then, if I ask you what is theta, what is the answer? So let me show it more properly. So this angle that you see here is alpha. But you are looking for the blue angle. So what's that? Pi plus pi over 3. So you calculate 4 pi over 3. So the argument of this complex number is 4 pi over 3. So if I want to summarize that, I don't want you to memorize things, but you can use it like this. You can say that, okay, alpha, you can always calculate it using this formula, the imaginary part of z divided by the real part of z. Yes? And then if the number is located in the first quadrant, theta is exactly equal to alpha. Yes? If it is in the second quadrant, theta is not exactly equal to alpha, but theta is pi minus alpha. So I don't want you to memorize it, but anyway, it will work. So you can write pi minus alpha. So you always find alpha from this formula. And if it is in the first quadrant, theta and alpha are the same. If it is in the second quadrant, theta is pi minus alpha. If it is in the third quadrant, as this example reveals, it is pi plus alpha. And what do you think will happen there? 2 pi minus alpha, not minus alpha, because minus alpha will not be according to that convention. So it becomes 2 pi minus alpha. So if you want, you can have this picture. It will always solve the problems, okay? Yes, but might be you forget, so it is better to understand what to do. Is that clear?
Yes.
Okay. Now that we understood the notion of the argument, what we do, we want to talk about the polar form. Okay, so let me just see that what the polar form is. Let us go back here. I have my complex number a plus bi, and I want to see what happens if I go to the polar form. And then if you don't mind, let me put the article they here, and I will discuss about this. Then I want to answer this question. What is the meaning of that? Yes, it means use trigonometry mainly, only. So what you should do, I just prove it for the case that it is in the first quadrant. You have to be able to convince yourself that it works for all points on the plane. So let us say that this is the real part and this is the imaginary part, and then I will find my z, and then I connect it here. I told you the absolute value in this context is denoted by this r, and this angle theta is your argument. Okay? But now if I ask you what is a, it is very simple, yes? What is this length? It is a. What is this length? It is b. If I ask you what is sine of theta, what is your answer? Sine is the opposite side divided by the hypotenuse, which is b over r. This means that b is r sine theta. And then cosine theta is the adjacent side, a, divided by the hypotenuse r. So this means that a is r cosine theta. Yes? And then what I do, instead of a, I put this, and instead of b, I put this. What I get is called the polar form. As simple as that. So what I do, I will write that z, my complex number, is a plus bi. What is a? A is r cosine theta. What is B? Is r sine theta, and then multiplied by I. And then you can immediately see that I can factor r out. So what happens? It becomes r. From here, cosine theta is left. From here, sine theta times I is left. Because I don't want to put this dot all the time, so I put I on the left side. Yes? So that is called the polar form or trigonometric form of the complex number. So what I am making it more complicated, yes? Because this form that I started with is simpler than the form that I get it. But I told you that the trade-off is that when you want to raise it to high powers, the polar form will help you much more suitable. Okay, so this is in the formula sheet, of course. So if I give you a complex number and I ask you to find it in the polar form, you have two duties to do. One is to find r, one to find theta. And when you found them, put them in the formula and don't simplify it. Because if you simplify, you go back to the Cartesian form. That's the whole point. So here, z equals to a plus bi. R is the absolute value, and theta is the argument. And then z becomes equal to r cosine theta plus I sine theta. This is called the polar form. This formula is in the formula sheet, but we want to use it over and over again here in this lesson. Any questions? For example, let us go here, and I ask you to put I in the polar form. Okay? So can you tell me what to do? So for example, the question is this. Z equals to I want to write it in the polar form. What do I need? I need two ingredients. One, the absolute value of Z. So what is the absolute value of I? Absolute value of I, either you use algebraic formula to calculate it, or interpret it as the distance from the point to the origin. Where I is here. What is the distance from I to the origin? 1. So the absolute value for this problem is 1. What is the theta for this problem? We did it before on the board. You can also immediately visualize it. So what is the argument for I? It was pi over 2. Do you agree? So it is just pi over 2. And then you put these numbers in the formula. So z becomes what? 1 cosine of pi over 2 plus I sine pi over 2. Be careful, don't put the numbers in. Because if you put the numbers in, you go back to I. Because cosine of pi over 2 is 0. Sine of pi over 2 is 1. So it becomes 0 plus I times 1, which is I. And it is good. It's not inconsistent, but the point is that we want to make it more complicated. So don't make it complicated and then simplify it, because if you simplify it back, you get the same number. So that is not the logic. The logic is to make it complicated. Okay? But of course, I don't need to write 1. What can I write? Simply, I can say z is equal to cosine pi over 2 plus I sine pi over 2. I haven't shown you practically what is the benefit of writing simple I in more complicated way. But I told you why it is useful, and we will see it in practice later. Any questions? Okay, for example, we don't need to solve all the problems. Let me just do minus 5. If I give you minus 5 and I ask you to put it in the polar form, so what you need to do, you need to calculate absolute value. What is the absolute value of minus 5? 5. And what is the argument of minus 5? No, argument. Pi. You said pi, yes. Pi. Okay, and then what do? You write z is equal to r, which is 5, times cosine of pi plus I sine of pi. And you will stop there without simplification, because if you simplify, you go back to minus 5. Why is that? Check. Cosine of pi is minus 1, sine of pi is 0, so if you multiply it becomes minus 5. Okay, so now one thing you learn is that if you have the polar form, might be they ask you to write it in Cartesian form or the standard form. What do? For example, let us pretend that you didn't know this. I have given you this and I ask you to put it in a standard form. What do? You just simply calculate. Okay, if these angles are famous, use the table. If the angles are not famous, use the calculator. And then you simplify, it becomes a number in its standard form. Yes or no? Okay. For example, let us do one more. Let us do this one. If I ask you to write this in the polar form, what do? So let me clean this. If I ask you to write this in the polar form, z equals to -1 minus the square root of 3i, and then I have to calculate r first. Here, this is the first time that I really need to calculate r using the algebraic formula. So what is the real r here? It's a square root of. So you could use these formulas for those cases as well, but because they were so evident, I didn't want to calculate it using the formula. But here I have to. So it becomes the real part to the power of 2 plus the imaginary part to the power of 2. And then what happens here? It becomes square root of 1 plus 3. It becomes square root of 4, and it becomes exactly 2. So r is found. Theta is the solution to this problem. So what does it mean? It means that if I give you this in the exam, what you see here on the board is part of the solution to this problem as well. So you will do that to find theta, but because I have already done that, I just use it. Otherwise, you have to put this solution for this problem. And then what do you write? You write z is equal to absolute value of z, which is 2, and then multiplied by cosine 4 pi over 3 plus I sine 4 pi over 3. And that's the answer. Okay? Is that clear? Okay. So far I have talked about the polar form. We can also talk about a polar form. Okay. So usually they cannot ask you to find a polar form because people can have different answers. Okay. This is why if they want to test your understanding about the polar form, they use it with the article there. So it means that you have to respect the convention up there. So you have to use this angle. And this is also very important to know that this number is going to play the role of the absolute value, so it should be positive. Okay? And by the way, the only complex number that does not have any polar forms is which number? There is 0. Why is that? Because for complex number 0, where is 0? 0 is at the origin. And then I do not have any vectors associated to that. So the notion of the angle between the vector and the real axis loses sense. So you remember, for the complex number absolute value 0, we do not have any polar forms. Okay? Okay, now let us talk about a polar form. You know, you have to remember this combination somehow. Cosine of an angle plus I sine of the same angle, that is important, multiplied by a positive number. This can be considered a polar form. You can also have a little bit of deviations here. For example, I might write something like this. So let me write it like that. So z is equal to, let me write -3, and then let me write here cosine of pi over 3 minus I sine pi over 3. Yes? Definitely this cannot be the polar form. Why? 2 reasons. One is that this is negative. Okay? The other scenario is that instead of having positive, I have a negative sign. But it is not that far off from being a polar form, yes? Because at least that is the same combination of cosine and sine with the same angles. I will also consider this a polar form. Why is that this is good to have this as a polar form? Is because I told you the goal of learning this topic is to be able to raise a complex number to for example, to power 100. So if your goal is to raise a complex number to power 100, you don't have to have the polar form. A polar form is enough. Whatever you can do with the polar form, you can do it with a polar form. Okay? So that is why I wouldn't say this is very bad to have it. But I want you to understand this is not the polar form because it is not exactly according to the pattern. The pattern tells you that this should be positive and these two angles should be the same. Of course, they are the same in this case, but this side should also be positive. So let us try to practice a little bit. If I give you this number and I ask you to put this in the polar form, what do you do? I mean, according to the standard definition of the polar form. If you want to do that, one way is to do what? Yes?
Simplify, calculate the number, and then
Yes, so you have to go to a standard form in general and come back again. Yes, so what, for example, this is the standard way of doing it. Might be this is not optimal way in this case, but we can do it in that way. Because is this a complex number? Yes, it is because of the existence of I. Yes? By the way, if I ask you what is the real part of this complex number, what is your answer?
-3 cosine.
Yes, because you multiply this in, that number plays the role of the real part, and you multiply this in, that number plays the role of the imaginary part. Okay, so let us just do that. So -3 cosine pi over 3, and then plus I 3 times sine pi over 3. But cosine pi over 3, I have it in my memory, it's 1/2, so it becomes -3/2. And then this is a square root of 3 over 2, so it becomes plus 3 square root of 3 over 2i. This is your complex number in a standard form. And then if you insist, you can switch back to the polar form, to the real polar form, yes? How should I do that? I need to calculate the absolute value. What is the absolute value? Is the square root of this number to power 2 is 9 over 4, plus this number to power 2 is 27 over 4. And it becomes 36 over 4. It becomes what? 3. Yes? So, 36 over 4 is 9. Square root of 9 is 3. Okay, and then what should I find for the argument? So the argument, you calculate tangent alpha. What is tangent alpha? Is this number divided by that number absolute value. So it is 3 square root of 3 over 2 divided by -3 over 2. So the answer becomes what? The square root of 3. So then alpha becomes 60 degrees or pi over 3. But this is not definitely the argument, because in which quadrant this is, the real part is negative, the imaginary part is positive, so I am the second quadrant. So theta is not alpha, theta is pi minus alpha. Yes? So what happens for theta? Theta becomes pi minus alpha, which is 2 pi over 3. So if I ask you to write this number, which I still believe it's a polar form, if I insist you to write it in the polar form, what do you write? Absolute value, 3, and then cosine. Instead of pi over 3, I put 2 pi over 3 plus I sine 2 pi over 3. So I found the absolute value, and I found the argument, so I was able to write it like that. Yes? So that is the polar form. Okay? But might be, if you're good in trigonometry, in this case, you didn't need to go back and forth. So I don't know how much you remember from trigonometry lesson. So when you multiply this here, you already know that you want to get this positive sign is good. I want to have it positive. But this positive sign is not good. So I want to get rid of this positive sign. Do you remember a trick in trigonometry that allows me to get rid of that minus sign? Yeah, it was the cosine of the complement angle. Yes. So the cosine of the complement angle is negative of the cosine of the angle. Sine of the complement of the angle is equal to the sine of the angle. So that's good, because here, instead of, what is the complement of pi over 3? The complement of pi over 3 is exactly on the board. So this is why, if you understood a little bit, if you remember your trigonometry lesson, you don't need to switch back and forth here. Instead of that, you just write positive 3 cosine of 2 pi over 3, positive 3 sine of 2 pi over 3. Okay, so you don't need to go back and forth. But let me ask you another question. Do you think that this is apolar form or not? I am going to write it. Let us keep it for a moment. So for example, let me write, I don't know, z equals to 2, and I would write it as minus cosine pi over 4, and then plus or minus I sine of, let us say, pi over 3. Okay? So you see here, I told you that even though this is dipolar form, but this can also be considered as apolar form because it is not that far off. The important thing is that I want to have the angles the same. I want to have a cosine, I want to have a sine, but I want to also have, the important thing is that the angles should be the same. But can I say that this is a polar form? Even though it deals with trigonometric relations, but I don't like to call it a polar form because
Angles are not the same.
the angles are not the same. Okay? So it is not even a polar form. So if I want to raise this to power 100, this is not suitable at all. I want to have the combination of cosine and sine with the same angle. Okay? So I want to wait for you to see that how can you put this in the polar form. Okay, so what happens? Of course, you cannot calculate it exactly. You have to use the calculator, but let us see what we should do. Tell me what to do first. I give you a number, complex number. I ask you to write this in the polar form. It is not even in a polar form because these angles are different. So what should I do? To open up the brackets. So, for example, I refer to the table. Cosine of pi over 4 is the square root of 2 over 2. I have a negative sign, minus I. Sine of pi over 3 is the square root of 3 over 2. Yes? And then I multiply this number in, so it becomes minus the square root of 2 minus the square root of 3 times I. That's your complex number in a standard form. Now, we can immediately ignore what I had so far. I concentrate here and I solve those problems that we solved on the board. So we switch to the polar form. To switch to the polar form, I need two pieces of information. One of them is R, which is the absolute value of Z. For absolute value Z, I have a formula. The square root of the real part squared plus the imaginary part squared. Yes? But then this becomes square root of, this number is positive 2, positive 3. The answer is a square root of 5. So that's my absolute value. But for the argument, I always use this idea. So I calculate tangent alpha according to the formula that I told you, the imaginary part divided by the real part. So this becomes absolute value of what? Instead of imaginary part, I put minus the square root of 3. Instead of real part, I put minus 2. And unfortunately, this is not a famous number. So it is just simply a square root of 3 over a square root of 2. But which angle is this? I don't know. The only thing that I can do is just write alpha is tangent inverse of that number. And I can write it as 1 square root. This is alpha. But what is theta? If you have calculator available and it is demanded to calculate up to some decimal points, you put this in the calculator. Otherwise, you keep it like this. But what is theta here? Can you tell me? For theta, you need to know where this point is located. The real part is negative, the imaginary part is negative, so it is in the third quadrant. In the third quadrant, theta that you're supposed to find is pi more than alpha. Okay? So this means that your pi is equal, your theta is equal to pi plus this number, whatever this is. So let me tangent inverse of the square root of 3 over 2. Okay, so if you want to write it at the end, you would say that the complex number z is absolute value of z, square root of 5, times cosine of theta. Theta is pi plus tangent inverse of the square root of 3 over 2 plus I sine pi plus tangent inverse of the square root of 3 over 2. That's the polar form of this complex number. But don't let this distract you. At the end of the day, this is a number. You can put it in the calculator and find it, whatever it is. Any questions? Okay, so sometimes the books write this in this way. If I want to write the complex number z in the polar form in a way that what you see on the right only have letter z inside. So what do I write? Oh, you already know. The polar form starts from r. But what is r? In terms of z itself, r is the name we give to the absolute value. So some books, they write it in that way. Cosine. What should I write instead of theta? I want to write something in terms of letter z for theta. What is theta named? What is theta? Argument, yes? You just write argument of z plus I sine argument of z. So some books write the polar form in this form. But that is understandable. Why? Because when you have a formula, what you have on the left should be expressed in terms of what you have on the left. And that's the formula, expressed in terms of what you have on the left. That's sometimes they write. One more thing. If theta is an angle, what is the absolute value of this combination that appears in the polar form? If I ask you, theta is an angle, I don't know what that is, but I ask you, first of all, do you agree that this is also a standard form? If you imagine this as a standard form, then you can say, what is the real part? Cosine theta. What's the imaginary part? Sine theta. So if I ask you, what is the absolute value of this complex number for some value of theta? What's the answer? Yes?
1.
1. Why? Because the absolute value is the square root of the real part squared plus the imaginary part squared. But this is famous. The answer is 1. So remember, this combination is a nice combination both in physics and mathematics. Mathematicians call this a unimodular complex number. Unimodular means a complex number whose absolute value is 1. Physicists call this a phase. In physics books, when you see they are talking about a phase in the complex number context, they mean a unimodular complex number. Okay, so remember that for every theta, the absolute value of this complex number is 1. So in other words, for any choice of theta, where do you think this will live? On the complex plane. Yes? On the unit circle. Because for any choice of theta, this becomes a complex number whose absolute value is 1. So it means for any choice of theta, the distance from this number to the center is 1 unit. So it lives on the unit circle. So if you see this as a moving particle, yes, by changing theta, this particle starts tracing the unit circle. Yes? If I start from 0, if theta is 0, this is 1, this is 0, the particle is here. When I start increasing theta, my particle moves counterclockwise in that direction. Okay, so that is good to know, that this is can be interpreted as a moving particle. Any questions so far? Okay, now the next part of the lesson is that what is the benefit of having a complex number in the polar form? If you want to add or subtract two numbers, there is no benefit to it at all. It's even make the problem more complicated, yes? So let us see what is going to happen. Now let us say that I have two complex numbers in the polar form, yes? So let us write z number 1 to be r1 cosine theta 1 plus I sine theta 1. Let us say someone gave me a complex number in its polar form and another number in its polar form. Yes? If I want to add them or subtract them, it is not beneficial at all to have it in polar form. It makes life harder. But if you want, you can do it, yes? So if I say what is z1 plus z2, you simply multiply this in, and start adding them up. When you add them up, the real parts will add. So that is theta 2, sorry. Oh, I made a mistake, sorry. Theta 1, theta 1, theta 2, theta 2, yes. So then I will add them like this. This becomes the real part of my number. And then I multiply them in, add them up, factor an I out, so it becomes r1 sine theta 1 plus r2 sine theta 2, and then I have I. So you see there is no benefit in doing it in this way. So this is why if your goal is to add and subtract, don't bother to go to polar form, because it makes life harder. Okay? If you want to subtract, you just subtract. But something interesting happens if I want to multiply and divide. And that's the reason. So polar forms are good if you want to multiply or divide. Okay, so let us try to understand why this is good if I want to multiply them. Okay, so if I want to multiply them, I can multiply them. The algebra is the same. So I multiply r1 by r2. I also take this one and multiply it by this one. Yes? I don't know why I make this mistake. This is theta 1. And then I multiply it by that one. Yes? But now let us do the algebra once for all. It's something interesting happens, you will see. So r1, r2, I keep it as it is, but I have to start multiplying as usual. I take this one, multiply it here and there. I take this one, multiply it here and there, and then add them up. So let us just do it. Cosine, cosine, it becomes cosine theta 1, cosine theta 2. This one multiplied by that one is I cosine theta 1, sine theta 2. This one multiplied by that one is I sine theta 1, but cosine theta 2. And finally, when I multiply this by that, I have an I here, another I there, it becomes I squared, but we know I squared is negative 1, so that's why I put negative, and then sine theta 1, sine theta 2. Yes? But now let us collect them. This is without I, this is also without I. I put them next to each other, and these two terms they have an I factor it out, as usual, okay? So this becomes what? R1, R2. I write cosine theta 1, cosine theta 2. The last one, I write it immediately after this one. Yes? This is the collection of these two terms. Between these two, I factor an I out. So if you don't mind, let me write I on the right. If I factor an I out, let me write this first. It becomes sine theta 1 cosine theta 2 plus this combination, which if you don't mind, let me write sine theta 2 first. That's a product, it doesn't matter. I hope that you remember a little bit from trigonometry lesson that these two formulas are familiar, at least to us. Do you see what that is? This formula is in which topic of trigonometry? You don't need to remember which one is that, but there was a lesson for it. This combination, is it familiar? Cosine of the first one, cosine of the second one, minus the sine of the first one, sine of the second one, for this part. Sine of the first one, cosine of the second one, plus the other way around, sine of the second one, cosine of the first one. We studied that when we were talking about addition and subtraction formulas of sine and cosine. Okay, so if you have forgotten that, if you check the formulas, this is the addition formula for cosine, and that is the addition formula for sine. So if you use those formulas, this becomes equal to R1, R2, and then I can write cosine, addition formula for cosine, plus I, addition formula for sine. So the only thing that I did, instead of putting I on the left, on the right, I put it on the left. So isn't it interesting? So a nice thing happens, yes? If my goal is to add and subtract, polar form is not useful. I'm making life harder for myself. But if I want to multiply, this multiplication, you don't do it at all anyway. I just wanted to prove it to you that this works. But that is the formula in the formula sheet. So, but the interpretation, the message behind the formula is very important. This is telling you, this formula, if you have two complex numbers in the polar form, if you multiply them, the rule is this: simply multiply absolute values and put it here, but add the angles and put them in front of sine and cosine. So it means that if I have two complex numbers in the polar form and I multiply it, do you agree this is still in the polar form? But you can give the rule, for example, you can call it in your head capital R, and you can call this in your head capital theta. But look, what is the structure? The structure is a number, positive, multiplied by cosine of this, plus I sine of that. Okay, so what happens if I have two complex numbers in the polar form? When I multiply them, automatically, using this formula, it becomes in the polar form again. But if I ask you what is the absolute value of the new complex number, how is it related to these absolute values? You will tell me the new absolute value is the product of the old absolute values. But the argument, the new argument, is not the product of the arguments, is the sum of the arguments. Yes? And that is the hard part. This will so it means that somehow this was the hard part, but not for this combination. For very particular case of complex numbers, which is a phase, if you have this combination, multiplication of a bunch of them is extremely simple. Okay? When I multiply them, the structure retains itself, but the angles are added. So you don't need to do any multiplications. Do you understand what I'm saying? Okay, for example, if I give you a complex number in this form, so let us say that I have 5. Let me write it in degrees because it is easier for us now. So let me write cosine of 89 degrees plus I sine 89 degrees. If I ask you what is this, you will tell me this is a complex number written in the polar form. Do you see the combination? That's exactly the same structure. But if I ask you, do you know exact location of this point? You would say no, because I don't know exactly cosine of 89 degrees. I can approximate it. I can find the approximate location, but not the exact location. But let me give you another complex number. Let me write this Z1. Let me give you another complex number Z2. So let me write it as 3. And then I would write cosine 1 degrees plus I sine 1 degrees. The same scenario for this. I cannot exactly find the location of this point. But if I ask you, is this a polar form? You would say yes, because that's the right structure. But if I ask you, what is Z1, Z2? You can immediately answer that. Because I have two complex numbers in the polar form, and if I want to multiply them, I read the message. The message is to multiply the absolute values, which becomes 15, but add the angles. So it means that you write cosine, you write I sine, but you add this angle to that angle. So 89 degrees plus 1 degree, and then 89 degrees plus 1 degree. Yes? But can I go further? In this case, yes. Why? Because this becomes 90 degrees, and then plus I sine 90 degrees. Okay? So, you usually don't like to keep it in the polar form. Polar form is a intermediate step that you go from a standard one to the complex form, do the calculations in the, you go from the standard form to the polar form, do the calculations in the polar form, and if possible, switch back to the standard form. Because at the end of the day, what I care is the standard form. Okay? So what is the answer to this? Cosine of 90 degrees is 0. Sine of 90 degrees is 1. So it becomes exactly 15i. Exactly, not approximately. So whenever you want to multiply complex numbers, of course, I'm not saying that whenever you want to multiply two complex numbers, switch to the polar form, because multiplication of two complex numbers is also extremely simple. But if I want to multiply, for example, 15 complex numbers, of course you can multiply 15 times, but you can also switch those complex numbers to polar forms and then simply multiply the absolute values but add the arguments. Okay? So here, addition is easier for us to do than multiplication. Any questions? Okay. So remember this. The message is that if I have two complex numbers in the polar form, if I want to multiply them, I can always switch back to the standard form, do the multiplication in that form. But other way is that just use this formula is in the formula sheet as well. So you just multiply the real part, the absolute values, and then you add the angles. Okay, now you see why this is useful. Because what happens if I give you one single complex number, say r cosine theta plus I sine theta. If I ask you what is z squared, I'm raising it to power 2 now. So z squared means multiplying z by itself. So what was the message? The message is that if you want to multiply two complex numbers in the polar form, multiply their absolute values. But because these two numbers are the same, the absolute values are both equal to r. So if you multiply them, it becomes r squared. And then you have to add what? The arguments. The argument of this one is theta. The argument of the second one, because this is the same number, is again theta. So it means that I have add theta to theta. Yes? But what is theta plus theta? It's just 2 theta. So it becomes what? R squared sine of 2 theta. Oh, sorry, cosine of 2 theta. And then plus I sine of 2 theta. Yes or no? Let me ask you to calculate z to the power of 3. So what is z to power 3? Z to power 3 can be interpreted as z to power 2 multiplied by one more z. But do I know z squared? Yes. This is my z squared in front of me, and I want to multiply it by z. What was the message? The message was to multiply the absolute values. The absolute value for z is this r, but the absolute value of z squared is r squared. I multiply them, it becomes r cubed. Yes? But now I add the arguments. The argument of this number is theta, the argument of this one is 2 theta. When I add them, it becomes 3 theta. Yes, so it becomes what? Cosine 3 theta plus I sine 3 theta. In principle, I have to use mathematical induction, but this is a Math 4 lesson. Some of you don't have mathematical induction. In general, I can prove that this idea of z to power n becomes what? can you guess what will happen?
Or
R to power n, yes. But the whole hard part is to raise this to power n. But this polar form tells me instead of raising it to power n, this is a very particular combination in complex numbers. If you raise it to power n, the final answer becomes n theta plus I sine n theta. Yes? And then you see, I want you to understand, this is a very important and powerful tool, because if I ask you, if I give you z equals to cosine theta plus I sine theta, and I ask you to calculate z to power 100, what does it mean? In principle, that is not a hard problem. It's complicated, but not complex, yes? So here, you raise it to power 100. In principle, there is no way in general, unless to write this 100 times and multiply. But this combination is an exception in complex numbers, and you have to remember it's 4. Okay? Whenever you have cosine and I, if you suffer and do all those calculations, according to what we showed, you end up with simply multiplying 100 there. I want you to understand exactly what is going on. Yes? The problem is that if I write this very particular combination 100 times and suffer to multiply them, simplify them, at the very end, the answer becomes this. Just simply multiplying 100 by theta. And that is the reason we suffer a little bit to go from an innocent complex number to its polar form. So it is useful if I want to raise it to high powers. For example, let me give you this question. Z, let us write it in this form. So let us write a square root of 3, and then let me write this 3i. I ask you to calculate z to power 600. Okay? So if you don't know this lesson, you should write this to the power of 600, and then you multiply it 600 times. Yes? But now, this is an indication. If you get a fairly high power in the national exam or in my exam, I am indirectly guiding you to use the polar form. Yes? Even if this angle is 6, even if this exponent is 6, even multiplying it 6 times, it involves 2 to the power of 6 terms, which is 64 terms. It's not that hard. I mean, 600 is very exaggeration, but even for 6, it is not that easy to multiply it 6 times. Okay, but how do you solve the problem? You see, because this is a high power, you have to remind today's lesson, and it means that you need to switch to the polar form. And then what you did in the beginning, we have to do it here. So how should I switch to the polar form? I need 2 ingredients. 1, the absolute value. 2, the argument. Yes? So the absolute value is what? Square root of this number to power 2 plus that number to power 2. So it is simply a square root of 12. You can keep it like this. Let us keep it like that. Square root of 12. And then the argument. Do you remember the formula I told you? Tangent of alpha is what? Is the absolute value of the imaginary part divided by the real part. If you simplify that, it becomes square root of 3. And then what do I get? I get alpha is pi over 3, 60 degrees. But what about theta? So do you remember this picture here? In which quadrant this number is? The first. In the first, theta and alpha are the same, if you have that the diagram in your notebook. So this means that all theta is the same as alpha. Okay, so everything is ready. Z is equal to absolute value, cosine of which angle? Pi over 3 plus I sine pi over 3. Agree? And now I want to raise it to power 600. What can I do? According to the rule, I have to take my square root, I have to take my absolute value and raise it to power 600. But the hard part is this one, which I don't need to suffer. I just need to multiply 600 by the angle. So it becomes cosine 600 multiplied by pi over 3 plus I sine 600 times pi over 3. Yes? But if this is possible to simplify, simplify it as much as possible. For example, what can I write for square root of 12 to the power of 600? I can simply write 12 to the power of 300. And of course, you shouldn't expect me to be able to write it down. That's enough to write it like this. But 600 times pi over 3, what happens? This and this is 200 pi's. And of course, the same true for the next one. But then, we know what are these, even without calculator. So what is cosine of 200 pi? So you need to know where 200 pi is. So you go one round, it is 2 pi. You go 2 rounds, it's 4 pi. You go 3 rounds, it is 6 pi. So you go how many rounds? 100 rounds, it becomes 200 pi. But it doesn't matter, you end up exactly at the point 0. So cosine of this is equal to cosine of 0, and sine of this is also sine of 0. But sine of 0 is 0, cosine of 0 is 1. So the answer to this is 12 to the power of 300. That's it. So you see, we were able to calculate it in fairly reasonable time, yes, without even calculator. So that is the power of the polar form, which I hope that you agree, that is at least good. You see, if the goal is to calculate this, polar form is really useful. So for multiplication and raising to power, and as the last part of the lesson, division, is also possible to do it in the polar form. Okay. Let me test your understanding geometrically now a little bit. That's also good. So, for example, let me tell you, I don't know. For example, I draw a circle with radius 1 over 2. Okay. And the center is the origin. And I just pick a point here, Z, and let us say that this angle I give you to be 30. Yes? Can you tell me where Z squared is? This is a good question. It's a conceptual question. You might face these questions in the national exam because they are not calculation and hard. They are asking you about your understanding. So let us say I draw a circle, but the radius of the circle is not 1, is 1/2. And I pick this point whose angle with the positive part of the real axis is 30 degrees. I can calculate Z squared, I can calculate Z cubed, and whatever. For example, let us concentrate on Z squared. Where do you think is a good, giving the address? If I want to know the location of Z squared, how do you give me the address? Yes?
It's on a circle with radius 1 to 4, and then the angle between the positive axis of the vector is
60 degrees. Yes, because I just told you because by looking at this picture, can you understand the polar form? Because for writing the polar form for Z, I need 2 ingredients. I need the absolute value, but I have it. Because absolute value geometrically means the distance from the point to the origin. And you have it because the circle has radius 1. So if I ask you what is the polar form of this complex number, everything you need, you have it on the picture. So it becomes 1/2, which is the absolute value. But what is the argument of my complex number? It's exactly 30 degrees. And then you know the rule. If I want to raise it to power 2, what happens? This should be raised to power 2, which gives me 1 over 4. But this should be multiplied by 2, so it gives me 60 degrees plus I sine 60 degrees. Okay, but now this is a new complex number in a new polar form. But if I ask you what is the absolute value of this, it's 1 over 4. But what is the argument? 60. So it means that where does this live? It lives on a circle whose radius is 1 over 4, and the argument is 60 degrees. So for example, if you have enough tools available, you can probably, this is 1/4, so you draw a circle. Yes, this is 1 over 4 here. It becomes smaller. And the angle, instead of 30 degrees, is 60 degrees. So this is, you find your point. Yes, that angle is 60 degrees. So this is where it is located. Yes or no? So these kind of things, it's good to know. Because it was not that easy, you know. When I was teaching you the complex plane, I told you that if z is there, where is IZ? Do you remember? IZ was the rotated version of z about the origin counterclockwise 90 degrees. Okay, I could ask you, where is z bar? You can answer this. By the way, if I give you two complex numbers, where is z1 plus z2? Okay, for example, let me give you two complex numbers here and here. So if I ask you geometrically, show me where z1 and z1 plus z2 is, here it is better to interpret it as vectors. Yes? So here this becomes z1, and then here it becomes z2. But you know how to add them, these two vectors. You complete a parallelogram, yes? And then you draw this diagonal. So here is z1 plus z2. Okay? But now, in the same spirit, if I give you a complex number here, and I ask you where is z squared, this picture was not useful. Yes? But this picture is useful. So if I give you this point, and I ask you where this is, so you will tell me, okay, if I want to imagine where it is, I connect it here. Whatever this angle is, I multiply it by 2. Yes? But then, what happens, it depends. I measure this distance and I square it. Yes? So this angle is this one, so I double it in size. And then I square this and find it on this line. If this is smaller than 1, when I square it, it becomes even smaller. And if it is 1, it remains 1. And if it is bigger than 1, it becomes even bigger when I square it. Yes? So that is the understanding that you should have back of your head, connecting geometry of the complex plane even more. So now you can have more tools in your hand to explore the geometry of the complex plane. Okay, so now I just want to write the formula for division. Let us see how we can do it. We can finish it. So let us at least finish this part. So for division, there is also a nice formula. So if I have those complex numbers on the board here, in polar form, this time I want to divide them. Yes? So this time, the rule is also very simple. You divide the absolute values. This time, instead of adding the angles, you subtract the angles. Okay, but which angle minus which angle? For cosine, it doesn't matter because cosine is not sensitive, but it is better to keep the order. The angle on the top minus the angle on the bottom, plus the same scenario for sine. Yes? So here, if I multiply them, I multiply the absolute values, I add the angles, but if I want to divide them, I divide the absolute values, I subtract the angles. And that's also in the formula sheet. Okay? I think I would just write this formula, but I will complete it next lesson. Of course, next lesson will be after the break. Okay? But hopefully you can watch the video before coming to the lesson so that don't forget about this. I need one more lesson to complete the exercises and everything in this topic. Any questions? Okay, so we stop here. Thank you.